Thank you for introduction. Okay. Shunsuke is not here today, so I will talk about our research this time. Hemodynamics plays a very important role for in the intracranial aneurysm initiation, growth, and rupture. So the accurate assessment of intracranial hemodynamics is very crucial. We expect that compared to 3T, high spatial resolution 4D4 imaging with the 70 MR imager might provide us with more accurate flow measurement for intracranial arteries. The purpose of our study was to investigate whether the accuracy of flow velocities obtained by a 70 device was better than those obtained by a 3T device in intracranial arteries. We performed the intracranial aneurysm silicon model experiment and healthy human volunteer study. We used an internal carotid artery posterior communicating artery aneurysm silicon model. And this is the ICA and the ACA and MCA, and you can see the aneurysm here. And we used the magnet pump and the Coreus flow meter. And we created the closed circuit, and this is the aneurysm model, and this was placed in a receiver coil, and the other equipment are placed in the operation room. And this is the reservoir, and we ran aqueous solution using this magnet pump, and these are the needle wave for flow adjustment. And we used the Coreus flow meter, and we measured the flow volume of each branches, and in one inlet and 3 outlet. And you can see the aneurysm here. And during the we performed the 4D flow imaging and 3D TOFMR imaging. And during the imaging, we measured the volume flow rate for each volume flow rate using a Coreus flow meter. And 10 healthy human volunteers are involved in this study, and we performed 4D flow imaging and 3D TOFMR imaging for the healthy human volunteer study. We used the 3T Tesla magnet and 7 Tesla magnet manufactured by Siemens. This slide shows the MR imaging parameters of intracranial aneurysm model and the voxel size. 3T Tesla, 7 Tesla, and voxel size these 0.5 isovoxel and 0.5 isovoxel and 0.35 isovoxel. No ECG gating, and the acquisition time is like this. This I show the MR imaging parameters of human healthy volunteers, and voxel size the same, and no ECG gating, and acquisition time is like this. We use this kind of software, hemodynamic analysis software, mesh creating software, and CFD analysis software, and statistical analysis software. This slide shows the process of magnetic resonance fluid dynamics using 4D flow dataset, and segmentation using region growing method, and mesh surface creation using marching cube method, and visualizing 3D velocity vectors. Next is a process of computational fluid dynamics. Based on this vessel geometry obtained by MRFD, we create a mesh in the vessel geometry. And the setting boundary conditions, we use these boundary conditions for the silicon model experiment. We use a volume flow rate of each vessel measured with flow meter, and for the human volunteer study, we use the volume flow rate of each vessel measured with MRFD. And we calculated the CFD. and obtained 3D velocity vectors. We calculated the 4 evaluation items. First is the correlation coefficient of for the magnitude of the velocity vectors of MRFD and CFD at the same coordinate points. And next is angular similarity index, ASI. It is the quantification of the degree of coincidence in direction of velocity vectors between MRFD and CFD. One is the best, and the equation is here. Next is magnitude similarity index, MSI. It is the quantification of the degree of coincidence in magnitude of velocity vectors between MRFD and CFD. And the equation is here, and one is the best. And the fourth is the SNR. We use the same region interest method. And I will show you the result of 3D velocity vectors of intracranial aneurysm model and MRFD or CFD, and these are the imaging conditions. 7 Tesla MRFD results show that the velocity vector distribution is similar to those of CFD near the vessel wall. But however, the 3D MRFD result show that the noise-like vector near the vessel. Please compare these two. Why? We thought that due to low SNR, 3D PCMR obtained by a 3T MR device has reduced the accuracy of flow velocity measurement in the low flow velocity region, resulting in velocity vectors closer to the noise level near the vessel wall. This slide shows the correlation coefficient of magnitude of flow velocities of intracranial aneurysm model. 3T 0.35 is showed the best higher velocities like this, followed by 70 0.5 and 0.5. This slide shows the correlation coefficient of healthy volunteer study. The result is the same. The first is 70 0.35, next is 70 0.5. This slide shows the ASI, MSI, and SNR of intracranial aneurysm model. 70 0.5 is shows the highest value, and second, followed by 70 0.35, and last is the 3T 0.5. And in the human volunteer studies, ASI of 10 healthy volunteers, there is statistical significant difference between these conditions. And as for MSI of 10 healthy volunteers, there is statistical significant difference between these two conditions and these two conditions. But please note that there is a different trend, ASI and MSI, because this one, like this, so the opposite trend. Why? We thought that in the analysis of the cerebral aneurysm model, the analysis region was the distal portion from the internal carotid artery C4 region. In the classification of volatility. On the other hand, due to sinus artifact, the analysis area of healthy human volunteer was the distal portion from the distal carotid artery, C7 area. So, therefore, the smaller arteries are included in human volunteers. So the caliber affected the final results. In conclusion, the blood flow velocity vector accuracy of the high spatial resolution with the 70 MR devices confirmed to be superior to that of the 3T MR device, suggesting the superiority of the 4D flow for intracranial arteries using the 7T MR device. Thank you very much for your kind attention.